Okay, so do you have any questions about the previous? I said it was. I did some performance tests with the hybrid MPI OpenMP traffic model, and I got some very strange results. So I don't I don't know if anyone else. I may have done something stupid, but I didn't get the results I expected. But I don't know if anyone that did some performance. I need to check up on that, but it compiles and it ran. It got the right answers. Yeah. Okay. So what combination of hybrid was that? You say hybrid, but it was.
So I took the MPI code and I just added a parallel do around the actual work loop.
And how many threads did you run on when you?
4 threads that was. Yeah, I didn't do any sort
so that's what I'd expect. Was that Fortran or C?
That was the Fortran code. I took the Fortran code.
Yes, so I did the C one. I think there's something funny with the C compiler. I think when you turn on OpenMP in C, it disinhibits some other options. So I think it turns off vectorization. So I think that I took a huge performance hit from simply the pure MPI code versus the hybrid code with one thread, which is the same thing, was a massive performance difference. And I think that what's happening is the C compiler is, when you turn on OpenMP, is turning off lots of optimizations. So the results didn't make any sense. But what you get there is exactly what I'd expect. That it runs a bit slower, but not terribly, and that's quite good because you're running on 2 nodes here, which has got minimal communications, and you're taking what, a 20% hit from putting in OpenMP. So that shows that it's not making it go any faster. It's clearly being done correctly, so it's not going any slower. So that's good. I think there's something gone funny with the C compiler. I should say that the traffic model is unfortunately not a very good code for measuring performance because it does integer arithmetic, and compilers are a bit patched. They do funny things with integers. With floating point operations, I understand what they do. They can have either blind spots because no one's ever really been bothered about optimizing large scale integer calculations, or they can do other things. They do crazy optimization. Okay, and again, Mark, was that Fortran or C? Fortran, yes, Fortran. So yes, so I live with this. There's clearly some issue with the C compiler. That makes sense. Okay, so yeah, okay, fine. That's interesting. Okay, thanks. So I will now. What I'm going to do is I did update the timetable. So if I should be better at working this thing. What I'm planning to do is I'll give this talk on RMA access and MPI. This might be a bit later, and then MPI shared memory. So people weren't particularly interested in single-sided communications. People were much more interested in the shared memory model. However, need to do some very basics. I need to do some basic. So the MPI shared memory model, which is actually probably more interesting than remote memory access, which are puts and gets, builds on some of the stuff that we do here. So I will do a very basic introduction to remote memory access, which is single-sided communications, put and get, i.e. a send without a receive or a receive without a send. But I will just cover the core bits which are relevant for the MPI shared memory model, which I think is more interesting and useful. So if I can just get the right thing to go. Fine, so remote memory access. So I'll basically talk about all the basics of RMA. I'll just set the theme, a bit of the terminology, a bit of the program flow. But the important point for the RMA remote memory access model in MPI introduces 2 new concepts. One are windows, and the other is synchronization with fences. And both of those are essential to understanding the shared memory model. So I want to enough so we can cover those, and then we can understand the shared memory model in the next lecture. So in what do I mean by single-sided? Well, message passing is fundamentally a two-sided operation. Every send has a receive. So it's pairwise, send and receive. So you need active participation of both sides. However, there are situations, even in message passing programming, where that's not convenient. So, for example, you may have a lot of data and you know where it needs to go, but you then have to tell everyone to receive that data, or you know where you want to read data from, you have to tell them to send it to you. It would be nice in a message passing model to be able to write directly to remote memory, or read directly from remote memory, i.e. do a send without there being a receive, or receive without there being a send. And this is possible using the RMA model. It's called put and get rather than send and receive. And what happens is that there is no matching. The remote process does not actively participate. So what you have is you have an origin process, and it can write data to the memory of a remote process. But to make that safe, or at least controllable, you don't want someone to be able to write to any of your memory. The way it works in MPI is you declare various memory regions called memory windows as being available for remote memory access. So you basically say you would declare a region of memory, which MPI now calls a window, and that makes that open to other processes either writing to or reading directly from that memory. However, synchronization is now a huge issue, okay? If someone's going to write data into that memory, is it okay? Have I finished with it? Or if someone's going to read data from that memory, how do they know that that memory is up to date? And that is never an issue in two-sided, because when you do a send and there's a receive, it's the remote process that actively decides when to receive that data and where to put it. And if you're expecting data from this process, it's this process that actively sends it. So you can never accidentally overwrite data or read data that's not up to date, because there's active participation of both ends. When you can write without a read, or write, so yes, that's a very good question. I will maybe come back to that. Yes, so I'll come back to that. That's a very, yes. So there are it's probably the synchronization that does that, but I'll come back to that. It's a very good question. So logically, the model is you write data without there being a receive, or you receive data without there being a send, but the implementation may be slightly different. So why is that? What is the motivation? The motivations are twofold. One is hardware. Many modern networks, things like InfiniBand or the Slingshot network on ARCHER2, actually at the very lowest level do actually allow you to read and write directly to remote memory. And so it'd be nice to exploit that in software. And also the software is that many algorithms are naturally single-sided. You know, a sparse matrix vector, you want to gather data from a vector, you know where you want to come from. You know, why can't you just read it? Why does the other guy have to send it to you? And you can do that with matching send and receive, but that requires extra programming. Now, often that's just an initial setup phase. So if you're doing a sparse matrix vector operation with a constant matrix, you can have a setup phase where you basically negotiate with all your peers who needs to send what data to what. However, if the communication structure changes at any point, if there's any kind of adaptive decomposition or something, then that's a nightmare, because every time that anything changes in the decomposition on the matrix, you have to redo this setup. So these one-sided communications functions are an interface to MPI remote memory access. So as we said, this comes back to what I think Stephen just said. One side is kind of a confusing term. Because there are other calls. So although you say you're not actively participating, there are synchronization calls. So the remote process has to call various synchronization calls, and that is where the data transfer may actually happen. I have to say I'm not a fan of this model of programming, because in fact it has a lot of overheads. It tends not to be very efficient in MPI. But it does introduce the two concepts we'll need for the shared memory model, which are memory windows you need to understand, and fence synchronization. So terminology, you have to have different terminology because a single process can read or write to remote memory. So the origin is the process initiating the request. The origin is the person that performs the call, but the target is the process's memory is accessed. And so the origin is the person that makes the call, and the target is where the remote memory is accessed. And the data may go from the origin to the target, or the target to the origin, depending on whether you're doing a remote write or remote read. But the important point here is that all remote access is performed on windows of memory to make it safe. You don't want to be able anyone to be able to read or write to any memory. And there's a lot of terminology that goes here, which I won't have a chance to cover all of it. But sorry, somebody just walked around outside if you wondered why I was waving. What you have is that you have this called an epoch. So you have a couple of synchronization calls, and within those you do lots of remote reads and writes, and you don't know when they're going to complete. All you know is they complete when you do the final synchronization. And that is, I think, basically coming back to what Stephen said. It is possible that none of the data transfer actually happens to the final synchronization. So it may be that you do lots of reads and writes. You say, right, we're going to start a phase of the program where we're going to do remote memory access. We then do lots of remote reads and writes. They may happen, but they may not. They may just be queued up and happen at the end. So it very much depends. So basically, the RMA program flow is you collectively initialize a window. All the processes get together and say, this is the region of my memory which I'm going to make available for remote read and write. That is collectively called a window. So a window is kind of a global object, but actually each process has contributed their own memory to that window. And then what you do is you start an RMA epoch, which is, you can think of as a, we'll come back to that. You issue communication calls, and then you stop it, and then you can then free the window at the end. And then you can repeat that many times, but that's the way that it works. So these are the important points in terms of what we're going to do later. Window management, fences, and data movement. So we said that for basic safety, to allow some protection of your memory, to stop a process randomly scribbling over your memory, you have to create memory windows. And so I've only given, apologies, I've only given the C interfaces here because the number of Fortran programmers was dwindling away. Actually, quite a lot. So hopefully, there are absolutely equivalent interfaces for Fortran, but I've only given the C interfaces here. So if you want to create a window, what you do is you call this called MPI Win Create, okay? And you offer up a region of memory where you give it the base address and the size. So you might allocate a megabyte of memory, and so you would give the base address, and then you give this would be 1,000,000 bytes. This MPI AINT is, the size could be bigger than 2 to the 32. This might not be storeable in a normal MPI integer where you have these strange things called MPI AINTs. So what you do is you want to create a window. So you say, here's the address. This is how many bytes it contains. This displacement unit is the counting unit. So it all gets a bit hairy, but basically the displacement, if this window was going to be used for reading and writing doubles, the displacement unit would be 8 bytes. So this means that when you, MPI really tries not to talk about bytes, okay? So, but what you're going to do is we're going to say, I want to write this data into a certain offset, 5 units into this window, and that displacement is multiplied by this displacement unit. The reason, this all seems a bit overkill, but MPI in principle is designed to work on heterogeneous architectures where you have different computers with different operating systems, for example, different compilers. So although nobody does this, in principle, you could run MPI on a system where some of the computers used 4 bytes, they're integers, and some of the computers used 8 bytes. This allows you to do that portably, because when you access this memory window, you only ever say location 4, okay, and that's multiplied up by the local displacement. So if you're doing 4-byte integers, you say location 4 is 16 bytes in. If you've got 8 byte, now it's all a bit overkill because nobody actually runs on these kind of machines, but that's why you have to do it here, for portability. There's an info object which you can give hints into, but we'll not cover that. It's collective across a communicator. Think of that being as MPI com world, and then you get back a window. So what you're basically doing is you're allocating some memory. You're telling MPI, we've all allocated all this memory. Consider this collectively as a single window, and give me back a window object to refer to that in the future. So each process can specify completely different sizes, locations, and whatever. You can specify null. And there's a few other caveats, but that is the model. You allocate some memory, and then you tell MPI I want to do remote read and write to this memory, and it then becomes a window. So having created the window, you can then query them and free them and things. You are then going to need to do synchronization. So you need to do a synchronization because before anyone reads from that window, you want to make sure all the data is up to date, so they're reading correct data. And you want to synchronize to make sure at the end, if there's been any writes, so you need to do a synchronization before to make sure if anyone reads the data, then it's up to date. And you need synchronization at the end to make sure that any remote writes are completed. And the simplest way to do it is a fence. Okay. Now, there are various, but it's called MPI win fence. Think of it as a barrier. It's a barrier in 2 senses. It's a barrier in time, in that everyone waits, but it's also a barrier in the sense that all communications will be completed. It's very much, in fact, it's almost identical to an OpenMP barrier, but it works in distributed memory. But an MPI win fence is almost completely analogous to an OpenMP barrier. So what you do is, before you do any read and write, you do MPI win fence on the window. There's an assertion here, which again is a bunch of hints, which we might come back to. Then you do the communication calls here, and then you don't know if they've completed until you do a fence at the end. Okay, so it's very much like OpenMP barrier, lots of remote reads and writes, and a barrier, but it's called a fence. So the RME call cannot start until the first fence, and all the communications will block. So you only know these communications are completed after this fence. So within this, all the communications calls will do, which are called things like puts and gets, are actually non-blocking, and they not guaranteed to complete till the end here. So you can now. MPI single-sided, this put and get model has a lot of overheads, unfortunately. So the more hints you can give to MPI, the better. So what you can do, I mean, I'm not going to go into it in detail, but you can basically say when you start a communications, an epoch between 2 fences, you can tell MPI things like there will be no puts. Okay, so you might say that there's not. So I'm going to start an area of remote communications, remote memory access, but there will be no puts. Okay, there'll only be read, and that allows MPI to do various optimizations. And so there are a bunch you want to do here. They're hints. There's a lot of them. I'm not going to cover them here because they're not really important in terms of functionality. They're not particularly important in terms of the shared memory interface. But if you write a real MPI program using MPI put and get remote read and write, it's really important to get these hints correct, because the more information you give MPI, the more efficiently, the less it needs to worry about, the more efficiently it can implement these operations. So there's really 3 general calls you can do within to a memory window. You can get data with an MPI get, you can put data with an MPI put, or you can accumulate data. So you might want to increment a remote counter, so that would be an accumulate. Rather than writing data at the remote end, it's accumulator, it means it might be added. So you can do a remote memory add. Accumulate's a bit of a but the basic ones are put and get. Okay, so you can get data, which is a remote read, and you can put data. And so there are lots and lots of arguments to this, because you're sort of specifying both the send and receive arguments at the one place. So you're saying, I want to let's look at the put. It's a bit like a send. I want to put data, which is at this address, this amount of data, and this type to this target rank. Okay, so that's the sending. The send operator. I want to send this amount of data from this buffer, which is of this type. I want to send it to that rank. It's very much like a send, but unlike a send, you also have to say where it goes to the remote side. So you give it a window, and you say what the target displacement is. That is, how far into the window is it? I said this is multiplied up by the remote count, base size, target count, and the target data type. So this is like the send. This is like the receive. The send buffer is this thing here. The receive buffer is the window itself. And a get is the opposite. You read data from the window. The origin is where it's going locally. Apologies. This is the receive buffer. Origin address, origin count, origin data type. You're reading from this guy, and there's so in fact the parameters for the put and the get are identical, but the data transfer is in the put. The data goes from the origin address on the local calling processor into the window on the target processor, and then get it goes the other way. So that is the way it works. As I said, the target displacement is multiplied by the window displacement unit, and there's lots of caveats here, but I'm not going into the details because we're just trying to motivate the window usage really here. A generic simple approach is you declare the storage on each rank, which is maybe a malloc in C or an allocate in Fortran. You create a window including all that storage with MPI win create, and you may notice that unlike a normal MPI call, there is no communicator in this call. That's because the window already, you specify the communicator when you set up the window. So the window knows which communicator it's operative across. You then access outside of an exposure epoch, outside of a remote communicator, you can just read and write that data just like a normal array. Okay. However, when you want to communicate with another process, you have to do a win fence, lots of puts and gets, another win fence, and then you can you can now access the data locally. Okay. So you declare an array, you make it part of a window. If you're outside of a remote memory access region, you can just read and write data to that directly. But if you want to access the data in someone else's window, you have to do a synchronization, which is a fence, lots of puts and gets, and then another synchronization. So an example, it is slightly contrived, but it's worth going through. But what we're going to do here, now, apologies, my laptop seems to be discharging its connection. Yeah, okay, so I was worried I was going to run out of charge. Apologies, the charger had come loose. Okay, so what we're going to do here, it's based on the example from a lecture at Cornell that a colleague of mine found. What we're going to do is we're going to basically do a broadcast. Okay, so what we're going to do is we're going to have data on rank 0, which is called control buff. Okay, and then we're going to want that to be distributed to all processes on my buff. Now, the correct way to do this would be to an MPI broadcast. Okay, however, we're going to do it with with single-sided put and get, just as an illustrative example. Now, the first thing you have to decide whenever you do put and get is you could do two things here. You could have rank 0 put the data to all the other ranks, or you could have all the other ranks read the data from rank 0. What we're going to do here is we're going to read, all the other processes are going to read the data from rank 0, so they're going to use gets. So what we do is we declare a window, win-win. The control buff is the thing which is going to be the thing which is accessed remotely. My buff is just a local array where it ends up. So what we're going to do is we're going to create a window, and this is slightly unusual, slightly asymmetric. The window is only going to include data, the control buff on rank 0. So that's not a typical thing, nor it's a bit more symmetric than that. But we say we're doing a win create. Rank 0 does a win create of the control buff, which is this many bytes long, size of int times 20. The counting unit is integers, and we get back a window object. All the other processes who are just contribute zero data. So we have a window, but actually it only has data that is declared on rank 0. We then initialize the control buffer on rank 0. So we now at this point have data in the control buffer on rank 0, and we want everyone else to read it. And so what we need to do is you need to do lots of gets, okay? But we need to basically surround them by synchronization. So we need to do a fence here, okay? If we didn't have this fence, then there would be a danger that the gets could happen before the data was initialized. We need a fence here to say, look, everyone wait till rank 0 has initialized the data, then we can all read it. So we do an MPI win fence on the win, and just to show you, we're saying MPI mode no proceed. That's saying there have been no preceding RMA calls. So without that hint, this fence would conclude any previous RMA operations and start some new ones. So without that MPI mode no proceed, MPI we're going to have to check whether there were any preceding remote memory access actions here it needed to complete. We know there aren't any, so we can say you don't have to worry about anything that's going on beforehand. So that's a hint. There's a fence at the end, which we have another hint saying there's going to be nothing after this. But there you go on the win. So within these think of these as barriers. Within that, we say, well, if rank is not equal to 0, I get MPI get into my buff, which is local, 20 integers from rank 0, starting from position 0, and it's 20 integers. So that's effectively yeah. So this is and we're getting 20 integers from the window and putting them. Sorry, we're getting 20 integers from the window on rank 0, starting at the displacement 0, and putting them into an array of size 20 locally. So that's a slightly contrived example, but the main model is you do win fence, put and get, and win fence. So there's some technicality here which I don't. There's a technicality I don't want to go into, but the point is here that this makes sort of sense if you're doing communications between different nodes. Okay, so this would if the person issuing the get was on a different node, then clearly you need to do an MPI call. However, what you've done here is you've declared a shared object, this window, a logically, which is a shared object, a shared data space, but you are not allowed to read and write to that directly. Every time you read and write, you have to a function called MPI put and MPI get. On a node, that seems mad, okay? Because we know we're on a shared memory node. I have this concept for a shared memory object. We know that all the processors are on the same node. Why can't they just directly read and write to it? Why do they have to go through the overhead of doing an MPI call? And so what the shared memory interface does is it says, okay, we'll use the same setup calls, MPI win create, okay, to create these shared sections of memory, but on a node, you're allowed to directly read and write to them. You don't have to do all this overhead of put and get. So that's the link between the two. The original concept of Windows was and fences for synchronization was designed for this put get model, where you always access the memory with function calls, MPI put to write, MPI get to read. Then people said, well, that's crazy, because on a node, why can't I do it more efficiently if I don't read and write? So they extended it to allow you to do that. So it's a bit of a whirlwind tour, but I think the really important concepts are that what we're going to do for the MPI shared memory interface is we're going to declare data. We're going to collectively stitch that together into something called a window, which makes that data available for remote read and write. We're going to allow people to directly read and write that with just standard array operations, a direct memory access read and write. But again, we're going to need synchronization, so we're going to have to we would do a fence surrounding those operations. So the initial fence makes sure that everyone's ready, and the final fence completes all the remote reads and writes. So that's the logic for it. So it's a bit of a whirlwind tour, but hopefully that is, it was originally designed for using puts and gets, which work between nodes. It's been extended to allow you to do direct reads and write within a node, but using the same concept of fences and windows. So I hope that's a bit of a, see if there's a question here. And what if Project wants to put several objects in? There would have to be different windows. I think that's so when you do an MPI win create, you're only allowed to, there may be a way of adding data. I think there is some, yes, there's in the standard simple form I presented here, when you do an MPI win create, you have to say this is the data I want to be part of the window, and that's it. And if you wanted to add data, it'd have to be a different window. Yes, and so that's what do you mean by several objects? I don't quite. Do you mean different arrays, or do you mean as in mixed data types like?
Well, both really. So yes, maybe two different integer arrays, but you could maybe have integer and floats that you might want to be looking at.
You'd have to cut. So there is. So I'm not really expert of this. I only know really enough about the MPI put and get and this model to allow me to do shared memory stuff. There is some.
Just for the example of computational fluid dynamics, you might have pressures and densities and different floats representing different fields that you might want to explore.
Yeah, no, I appreciate that. I think that the okay, so I've just so you're absolutely right, but I think that what you want is, I think it's this. So it's taking a long time. I think you want MPI win create dynamic, which then allows you to use MPI win attach and MPI detach to add different pieces to that. I'm not 100% sure, but that I think that's correct. That MPI, this has been extended. MPI win create dynamic. It does what you like. You set up a window, but you can continually you can stitch lots of different arrays into that. I think that's probably what you're asking for, isn't it? I've not used it myself. I believe that would do what you want to do. I need to look at it in more detail to check.
Okay, I'll class that as advanced.
Yeah, well, it says however configured modifiable linked list using army operators. I think that's what it's saying. Yeah. I think that's what you want. But we need to have, yeah, that I think is what I was thinking about. If we do MPI win attach, I've not used these. Yes, there it is. Multiple non-overlapping memory regions may be attached to the same window. So I think MPI win, yeah, you do MPI win create dynamic and MPI win, and many cores of MPI win attach will allow you to do that. Does that make sense? I think that's kind of what you want. Yeah.
Okay, thanks.
Okay. Actually, I will actually cover the thing which I said with a bit of technicality because it is important. So I've now lost, I've been a bit of an idiot here. Okay, so there is now you can imagine the MPI people are kind of obsessed with portability. So you can imagine what you would expect is that when you create a window, you have a local piece of memory, you put it in a window. You'd expect when someone does a remote write to that, it goes straight into that window. You could imagine an implementation where that was not what happened. You could imagine that actually, when you do puts and gets, they went into some separate space, and at the end of the final synchronization, that data was copied to its final location. Okay, so what you can imagine is when you do puts and gets, they don't actually go to the ultimate destination. They're staged somewhere, then copied in. That's not going to help us when we do shared memory. Shared memory, we really want to read and write to the actual memory location. So MPI has a concept of public and private of whether it's has a concept of two possible implementations of RMA. One is called unified, and one is called separate. Now, so what the unified memory model means is when I write to a remote window, it actually goes into that memory. Separate means it might go somewhere else and be copied in later on. To be able to do direct read and write, we need the unified model. We want the window memory to be actually the memory, which is the real memory. We don't want it to be staged anywhere intermediately. The reason I said about a technical distinction is that I've never come across a situation where the model wasn't MPI win unified, but they're being paranoid about that. They're imagining a situation where you have a shared memory, a distributed memory machine where you can do remote memory access, but not to standard user memory, only to special regions of memory. So to implement MPI remote memory access, the library would have to do remote memory access into these special regions of memory, and then in a subsequent step, copy the data into the user memory. Now that modern Linux systems, that's not what happens. When you do direct read and write over a network, it goes to its ultimate location. So it is slightly of a technical concept, but just to be clear, for you to be able to do the MPI shared memory, the MPI library has to implement the unified MPI RMA model. But as far as I know, all MPI libraries do. So it's one of these questions of whether someone's proposed this standard and someone's gone, oh, what about this? And then they have to come up with some, I would call them weasel words to say, but in practice, all modern HPC systems use the unified model for RMA, which means that when you write data, it actually goes to where you want it to go to. It's not staged in some intermediate location. So there are, you can do other things for RMA. You can do locking and things like that, but I'm not going to cover that. That's a bit beyond that. I'm really only concerned with a very simple model where you do a global fence, lots of puts and gets, and then a global fence, and then it's over. So you delineate very clearly the regions of remote memory access between two fences. So the summary is the model's quite simple, although the syntax is quite challenging. Again, a lot of the complications in the syntax is this backwards compatibility that they want this to, in principle, be implementable on machines where node 0 uses 4 bytes for integers and node 1 uses 8 bytes. So there's all this additional complication. In practice, the performance may not be very good. The requirements of portability and stuff like for MPI, I mean, the latency of these puts and gets can be horrendous. However, Windows are a key component of the MPI shared memory approach, so that's why I have a lecture that covers them. So, you know, what we're going to do for the shared memory approach, we'll take a sort of 5-minute break before we do that, is that we'll allocate local memory, we'll do a win create to make it part of a global thing, and then we will be allowed to directly read and write to memory to Windows which run on the same node as us. We could do a put and a get, but it'll be infinitely faster to direct read and write. But we still need the fences to synchronize before and after that's done. So apologies, that was a bit of a whirlwind, but hopefully that means that we're set up, for the next lecture. So I'll stop there and take a short break, and then just have some cup of tea. Come back at let's come back at 1:30, just because I need to. I'm in a slightly remote location for this lecture, so even the small thing of getting myself a cup of tea is a bit of a thing. We've covered quite a lot there, and so I will. So I saw a comment, I think it was from Mark. Yes. So what you want to do for your performance of the hybrid MPI OpenMP is to have a graph where you always use a fixed number of cores, say 128, but at one extreme you have 128 MPI processors in one thread, then 64 MPI processors in two, 32 and 4, all the way up to 2 MPI processors and 64 threads, and 1 MPI processor, 128. And what you would do there in a real application is look for the sweet spot where you get the lowest runtime. I tried to do that for the C version and got bonkers results, because I think there's some strange interaction between the compiler and turning on threading, which gives you a large slowdown. However, for Fortran, it seems to be a lot more as I would expect, that you would expect to get. Well, you may never get any improvement, to be honest, because it's such a simple program. But you would definitely expect one thread and one process and 128 threads to be quite slow for a whole bunch of reasons. Anyway, we can look at that data later on. So we've got a 10-minute break, and I'll start again the RMA at 1:30, and then the exercise is basically I'll give you the solutions, but to look at doing the traffic model using RMA. So that is effectively doing the same as the hybrid MPI OpenMP, except that on a node, rather than using OpenMP parallel regions and shared arrays, you do the equivalent in MPI shared arrays, which are done through MPI Windows. But we'll cover that in the next lecture. So we got for C code 1 thread. Is that 0.1 or 0.1? That's what I got. So so that is weird, because that was not the case last year, I'm sure. So you're absolutely right. For some bizarre reason, compiling with OpenMP turned on and running with one thread is 7 or 8 times slower than not compiling with OpenMP at all. And I do not understand that. That is something I did not expect. So Ricky, so I wasn't going mad. You've got the same as me. That is not what we'd expect. It's some weird feature of the C compiler integers and OpenMP. I don't quite understand. Fortran seems to be a lot more reliable there. I will try and find out what the issue is, but that was a surprise to me. I've not seen that effect before, and I ran this course, I'm sure, a year ago and didn't see that. So yeah, thanks. At least that you've confirmed I'm not going mad. Okay. Okay, right. So I'll speak to you again in about 10 minutes with a fresh cup. So hi, Oh, there it is. I'm back again. Just checking out there, all okay on the audio. I assume it is. Not had any problems before. Okay, so what I'm going to talk about now is the MPI shared memory model. Since MPI process behaving as threads. So what I mean by this is, imagine you had a situation where you had a large lookup table, a sort of database, static. And in MPI, you would, for each MPI process to read that, you would have to have 128 copies on each node. It'd be much nicer to have just one copy on each node. You could try and do that with OpenMP, but that would mean that you would have to thread every single part of your code, because to do that you would run one MPI process per node, 128 threads. That would allow all threads to access the lookup table, but that means you have to thread your entire code. And so that is it. OpenMP and MPI allows MPI processes to spawn threads, but that is not always ideal. Here we have MPI process behaving as threads. So in this, using the MPI shared memory model, you could have a single copy of the lookup table on each node, and MPI processes could all just read that. And so that is why in certain situations it's a lot more convenient and a lot more of an incremental model that you can just alter small sections of the program to use shared memory to communicate rather than message passing, but you don't have to globally alter your whole code. And in hybrid MPI OpenMP, the global change is running fewer MPI processes than CPU cores. Here you run the same number of MPI processes if you ever would. So let's go through example. Oops, I've accidentally clicked something. So there's a bit of a motivation, which is something of a recap. I'll talk about shared window allocation and synchronization, which we've already covered a bit previously. But there's one other concept we need, which is to get node local communicators. And that's quite useful in other contexts. So we've talked about this in OpenMP, parallel regions, all threads access shared arrays. But why can't we do this with MPI processes? Okay, why do we have to spawn these regions to do that? So I would say that you need to be well. This is one of the problems about the consequences of MPI plus OpenMP is you started off with a pure MPI code here. Okay, right. So what you have to do is you have to start adding OpenMP. Okay, and so sorry. Take it back. What is the problem about the incremental approach of adding MPI to OpenMP? Let's imagine a simple example where instead of where you're going to run one MPI process per node. Okay, so immediately you say I'm going to use OpenMP, you have to unsubscribe the processes. So you take a huge hit in performance. Okay, so you say I'm going to start using MPI plus OpenMP. The first thing I need to do is to run fewer MPI processes than CPU cores, and you take a huge hit in performance. And then you start adding OpenMP to all the different loops, and you get faster and faster and faster, but you never know if you're going to actually beat the MPI performance so this is developer time. You add more and more OpenMP and hope to get up to there. Okay, so adding OpenMP to an MPI program is not incremental. Okay. However, in this shared memory model, you can do incrementally. You can introduce, well, this one routine I will implement using shared memory rather than message passing. So other use cases I've talked about are saving memory. As I said, some Met programs will allow static lookup tables and would allow us to do one copy per node. This NUMA-friendly memory allocation is really very technical and not really of any interest, but that was just a particular case I had once. But the main one is saving memory. So exploiting shared memory. With standard RMA, which we've just covered, you publish local memory collective shared window, you do read and write with MPI get and MPI put, and you add appropriate synchronization such as MPI win fence. But this seems wasteful on a node why can't all processes just read and write directly as you would in OpenMP? In OpenMP, you just do normal memory read operations to access shared data. What are the requirements? As I mentioned before, technically this requires a unified model where there's no distinction between RMA and local memory. I've never seen this. This is not a restriction in practice for standard CPU architectures. However, if you are concerned, you can query an attribute called MPI Win model and check it's set to MPI Win unified if you're paranoid about these things. But I don't think that's necessary in practice. That's all a bit of a preamble, which unfortunately I appreciate was a bit of a recap. But now we're going to talk about the procedure. So the first thing we're going to have to do is that clearly we're only going to be able to do read and write, direct shared memory read and write, if all the processes are on the same physical node. So we're going to need to create communicators which are local to a node. Because remember, window creation is collective across a communicator. So to do shared memory read and write, we're going to need windows which are only local to a node, which means to do that, we're going to need to create windows which are local to a node, which means we're going to have to create communicators which are local to a node. So previously we've never bothered about that, but now MPI actually has a nice way of saying, I would like to create I would like to split the communicator such that all the processes on the same node are in the same communicator. And that's actually useful. I mean, it's essential for doing MPI shared memory, because as I said, clearly you can only do direct memory read and write if you're all on the same node. It's actually useful in other contexts. So for example, if you're doing parallel, if you're doing I/O, then it can be very inefficient on large process counts for every process to read and write its own file. You can end up with hundreds of thousands of files, which completely kills the file system. It's much nicer to have one file per node for various reasons. So what you want to be able to do is identify all the MPI processes which are on the same node, and that is now easy to do. Okay. So but we'll cover that. So what we do is the first thing we do is we processes join separate communicators for each node. Then within each communicator, where we know that all the processes are on the same node, we do a shared array allocation of all processes on a node. Okay. And this, what we do, the way it works is that each process receives a local array. So if you have 128 processes, they all might want to say, look, I've got an 8 byte array. Okay. So each process is a local array, which is say 8 kilobytes long. But what actually happens is globally, across all 128 processes, the operating system allocated a single consecutive megabyte of memory and split it up into chunks. So we have this special shared allocation array, which means that although each process has its own local array, the operating system arrays, these local arrays are actually all parts of a single global array. Okay. And this may seem a bit bizarre, but you can do remote access by indexing outside the limits of your local array. So if you want to write the last element of the previous process, you just you access the array element local array -1, which it sounds a bit, yeah, it sounds a bit hairy, but it works. Okay, so normally, if you were to access outside of the bounds of your local array by going off the end or before the start, you get a segmentation fault. But because we've allocated the memory with this special shared memory allocation routine, if you want to access someone else's memory, you just over or under index on your local array. And we'll have a specific example of that. You need appropriate synchronization for remote accesses. You need to use fences around that. And again, this only works on a node. Clearly, for inter-node communication, you still have to do standard send and respond. You could use put and get, but you could use MPI for doing inter-node communication. But on a node, this is the procedure. You get your processes to join separate communicators for each node. There's a special array allocation routine called MPI Win Allocate Shared, which arranges for each process to get a piece of memory, but for globally then to be part of a unified single piece of global shared memory. That means you can access other people's data by indexing off the end of your own array, as long as you synchronize with MPI Win Fence. So maybe an example is the best way to illustrate this. So the first thing is to split the communicator, MPI. So they introduced a new routine called MPI com split type. So what you do is you give in the initial communicator, which here will be MPI com world. You then give a split type. Now, I can't remember, initially there was only one split type called MPI com type shared. So that was saying split the communication into sub pieces where all the processes on the same shared memory node are split together. Okay. However, going forward, you can see that there's a lot. The reason they didn't just have a single routine called MPI com split by shared memory node. They made a more generic routine called MPI com split type, where you specify the mode, the type of split you want. And you can imagine that in the future you might want to say, well, I've got a bunch of processes. Some of them are on nodes which have GPUs, some of them are on the nodes which don't have GPUs. I'd like to have two communicators, one which was the CPU node and one which was the GPU node. You would then call, they can extend this and do MPI com split type, where split type has accelerator or something like that. So it's a general routine. I've only ever used it for splitting by shared memory node. You specify a key. The key controls the rank order within the subcommunicator. So you're going to create a new communicator. You will have different ranks within that subcommunicator. On ARCHER2, the new communicator would always have 128 processes. So you'd be between 0 and 127, rank 0 and 127 on that local communicator. The key, if you specify the key as, I would specify the key as your global rank. That's the standard thing to do. And then info is a lot of other hints you can give here. I've never used, I just do MPI info now. You'd have to look at the manual to find out what these, you can give hints here to things you want to do. But MPI com split type is a relatively new routine introduced when the RMA interface came along to allow you to group all processes together that are on the same shared memory node. So that's the first thing you need to do. So for example, if I had I was running on two nodes, each which had 6 processes, my com words are size 12, and they might be allocated 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across the 2 nodes. If I did MPI com split type, MPI com world, MPI com type shared, this rank, so this governs how the processes are ordered in the new communicator. If I specify that as being their global rank, then they'll be ordered in the new communication the same way they were ordered before. Infinite, and I get back a new thing called node com. So within com world, I have size 12. The guys on the first node will be numbered 0, 1, 2, 3, 4, 5 in com world, and 0, 1, 2, 3, 4, 5 in node com. But on the second, on node 1, there'll be 6, 7, 8, 9, 10, 11 in com world, but 0, 1, 2, 3, 4, 5 in node com. Okay, so remember your rank is always actually local to your communicator because node com is of size 6. All processes will have ranks between 0 and 5 within node com. So does that? Oops, sorry. So yeah, so that's the first. If there are any questions on that, this called MPI com split type will create, in this situation, 2 communicators, each of which has 6 processes. Yes. I've never used MPI groups. So yes, one of the most generic ways to control what processes are in what communicator is to extract a group from a communicator, do various operations on those groups, and then reconstitute the communicator from the groups. I've never actually found any reason to do that. This is yes, you could do this with groups and things. The way you used to do it before this routine is every process would actually get the host name. So it would get the host name of the node that you were on, which would be a string, and all processes on the same node would have the same host name. So yeah, the way I do com column com row is I would do for row col stuff, I would do MPI create. I would create a Cartesian topology, and then having done that, you can split by. There are routines for splitting a Cartesian communicator by rows and columns called MPI cart split. I can't split that. I should remember. It's not split. MPI cart. I should have apologized about it. Cart sub. MPI cart sub. Sorry. MPI cart sub. Yeah. Sorry. That's no. It is. It is. Yes. So I've always found ways of not having to go to the complexity of groups. So for row call stuff, you can do an MPI cart create. I've got the capitalization on there. An MPI cart sub, which does sub communicators based on dimensions. But yes, the most general way is to manipulating groups. But you're right. The old way would have been to work out your host name, create groups based on those processes which have the same host name, i.e. lived on the same node, and then reconstitute the communicators. But that's quite a lot of effort. This is a simpler way of doing that. Then we need to create a shared array. Now, the model for normal RMA is you allocate the memory locally, and then you all offer that memory up, and MPI creates a single logical shared memory window out of that. Here we can't do that because we want each process to have, we want each process's local memory to be actually part of a contiguous block. So we can't allocate the memory and then make a group, make a window out of it. We have the window routine has to allocate the memory as well. So MPI when allocate shared does two things. It both creates the window but also allocates the memory. So what you do is you say, I want to have a shared memory window of this size. You give the same thing as the window displacement unit, and you get back the base pointer. Okay, so you don't provide the memory. You say, I want memory of this many bytes, and the MPI routine actually gives it back to you. So it gives you back two things. It gives you back the window, and also it gives you back the pointers to the memory it's allocated. Okay, and the same thing in Fortran. So size is the window size in bytes, displacement unit is the basic counting type, info, I always use MPI info null, the com is the parent com, and this will fail if some of the processes aren't in the same node. This will fail. If you try and do this on MPI com world, where MPI com world spans more than one node, it will say, no, I can't do it because not all these processes are on the same node. And the base pointer is the allocated storage, and the window is the allocated window. So MPI when create, you supply the storage, and it gives you back a window. MPI when allocate shares gives you both the storage and the window. And so to do the traffic model, okay, and that's why I think it's a useful thing to do, I do MPI node com. So I tend to call the communicator, which is node local node com. So we have on the previous example we mallocked old road. Okay, here I want to create it. So what I would do is I say int star old road, which is pointed to old road, MPI win node win. I have an MPI a and win size. This is the size of the window and a displacement unit. So the win size, remember my array has halos, so the win size is n local plus 2 times size of int. Unfortunately, I have to specify bytes here, but you're saying I want to have n local is the local size of the road. I want to have enough memory to store n local plus 2 integers here because I've still got these halos. The displacement unit is the size of int. That's 4. That's useful for the window. And we do MPI when I share the win size, which is how much data I want. Displacement unit, which which is size of int. The node com is, let's assume I previously created it, and it gives me back the old road and the window. So this attaches this amount of storage to that pointer here. In Fortran, it's a bit more hairy. Do I talk about that? I think I talk about it. If not, I'll come back to it. In Fortran, it's slightly hairier, but I will say how you do it. The problem in Fortran is that this returned value is just a memory address and not a Fortran array. So you need to jump through hoops to make it into a Fortran array. I'll come back to that. So if we did this call with n local equals 2, so imagine we call this with n local equals 2. The window size is now 4 because we need to have, we've got a tiny simulation. Every process only got 2 cells, but we have the halo, so everyone's got 4. If we all call MPI win allocate shared, and we say we want a window size of 4 integers, what the operating system does is it actually creates, imagine we're on 3 processes, it actually creates a global shared array of size 12, and on rank 0 it gets this data, on rank 1 it gets that data, and on rank 2 it gets that data. So you get how much data you asked for, you get 4 integers, that's the local road plus 2 halos, but the operating system has arranged for those to actually globally be passed off of the same array. So if this rank 1 was to access the array here, it just says that's x0, that's x minus 1, that's x3, that is x4 or x7. So it may make you feel a bit dirty, but you can access other people's memory by over-indexing or under-indexing your local array, because that is still valid memory. The default is continuous block of memory across processes. If you don't want that, you can say you can set the info object to allOpshed non-contig equals true to relax this. But I mean, to be honest, I don't see any point in doing that. The only uses I've ever had of this are when it's useful to have a globally contiguous large shared array. So there's a question there. What error does it throw me out on node rank 1? Well, it might. So it depends. It might. The way that might be a valid address which has junk data on it, or it might be an invalid address. It would give you a segmentation violation. It would give you a segmentation fault because you're accessing memory which doesn't exist, or hasn't really been allocated. So it would just be, it wouldn't be an MPI error. It would just be a normal. It would be, in fact, exactly the same error as you get if you indexed off a normal array. It would just be that data doesn't exist, which would be a segmentation. Accessing other ranks memory. In this previous diagram, rank 1 can access rank 0's x0 by reference zone x minus 4. Yeah, so rank 1 can access that by going x0, x minus 1, x minus 2, x minus 4. Fine, okay. It might be more convenient to access from. It might be more convenient to actually everyone to have a pointer which starts here. Okay, so you might say it would actually be nicer if we all just knew that address and could access to the right of it. For slightly weird what you would think you could do, why can't rank 0 just MPI send this address to everybody? Okay, it turns out because of the way that virtual memory works, that isn't guaranteed to work. So there is a special call. So if you want everyone, rather than over-indexing your local array, if you want to actually basically everyone just to know where the array starts on rank 0 and then start indexing to the right of that, you might say, well, rank 0 could MPI send its value of x, i.e. the value of the pointer to rank 1, but this will not work in general. The reason is so the virtual memory is when you specify addresses in a program, you're not specifying physical addresses. They're virtual memory addresses, and they're translated to physical addresses. So the normal situation is that the same virtual address on two processes can have different physical addresses. The corollary is that actually the same physical address can have different virtual addresses. So the operating system sometimes does this deliberately. Okay, that there are various hacks, security exploits, which are to do with buffer overflow hacking attacks, which Linux, it's something, I think it's called page randomization. Anyway, there are reasons which means that if you MPI send a memory address from one process to another, it may not be valid. And there's a very strange call called MPI win shared query, which says, can you give me a pointer which will give me access to the memory on another rank? It gives a local point we can use transfer memory. It's a slight corner case, but if you do want to know what the address of the array is on rank 0, you can't just get that to send it to you. You have to query the window because of some slight subtleties with virtual physical memory. I may have explained that slightly wrong, but so what we can do now is we can decide that. Now I've done something slightly strange here. Is I've kept the halos, so I'm still going to do communication between processes, but I'm going to do it by direct memory copy. You could, of course, you don't actually need to have the halos at all, but let's assume we're retaining the halos, and we're rather than doing an MPI send and receive to exchange that data, we're doing a copy. Okay, we would just say that we would say x0 would be equal to x minus 2. Okay, so we'd say, however, you need to do synchronization. You need to make sure that the worry is just like you have a worry in OpenMP. If you're reading and writing this data, what happens if this guy is also reading and writing to it? You might get a race condition. So you need to have synchronization, and you use the same MPI win fence as you would have in normal RMA. So what we do is we do an MPI win fence. We then do the halo swapping, which is all road of n lost local plus 2 is all road of n local, all road of -1 equals all road of 1. And then I do another win fence. What I'm doing here is I'm deciding to write the halos. Okay, so what I'm doing is here I'm writing my boundary data to my neighbor's halos. You could do the other way. You could read your neighbor's halo boundary data into your halo, but I'm doing a write here. So you bracket the remote accesses with a barrier, exactly like you would with OpenMP, except here it's MPI win fence. So you do a fence, everyone waits, we do various reads and writes, then we do a fence here. It's only after the fence that these are guaranteed to have taken place. So, sorry. Off-node comms, the direct read and write only work within a node. You still need MPI comms for internode, and so you need to do a send receive, and of course that has to take place in COM world because you need to, by definition, access or talk to processes that aren't on your node. Interestingly, it's just a bit of an observation, but if I want to send, if this is the data on a node and there's another node over here, I would maybe want to send that data to the next node along. The obvious thing is for this rank to do, but actually you could use any rank to do it. Rank 2 could send the data appropriate for rank 0. That would be a bit weird. The natural thing is to have the data. It's a very strange thing in shared memory MPI where you can actually now, any process could send and receive the data for another process. I would always have the process that owns the data doing the MPI calls to the next node, but in principle you could do it on any node, on any rank. So we still need, so again, you still have this split that you have two phases of your program. One is where you do off-node communication, and one where you do on-node. With MPI OpenMP, we did the on-node with OMP parallel and parallel 4, parallel 2. here we do it with these wint fences and these direct memory read and writes. So, the conclusion is it's a relatively simple syntax for shared memory and MPI. When I say it's better than raw your own solutions, before this shared memory interface existed, people would do this by hand by using things like POSIX shared memory segments. This is actually quite a simple way of doing it. The possible use cases are on-node communication without needing MPI, and one copy of any static data per node, not per process. The advantages are it's an incremental plug-and-play approach. So we could write a version of the update road which used pure MPI. We could write a version of update road that only used MPI for the off-node communications and used direct memory read and write for the on-node communications, and we could just decide at runtime which one we used. We don't have to make this global decision before we even launch the program of running fewer MPI processes than CPU cores. The disadvantages are you don't have all the support you have in OpenMP for splitting up parallel loops. And the other thing is that the global array may have Halo data sprinkled inside. So the nasty thing is, you can get around this, but the naive thing here is you can see that actually this is junk Halo data. So it can be a bit tricky, but I think it does have it. It does have its. Whoops, sorry. I'm being an idiot here. So I think it does have lots of potential useful use cases, in particular on one copy of static data per node, not per process. But if there's one thing which is, even if you never use RMA, the MPI com split type is actually a very useful routine. I've used it for parallel I/O, where I've wanted to have one file per node, not one file per process. And I said to do that, you need to identify all the processes that are on a node, and that it's a useful routine there. So even if you never use the RMA stuff, knowing the MPI com split type could automatically decompose your processes into subcommunicators based on whether they're on the same shared memory node or not is actually very useful, and I find it useful in a number of other contexts. So that's kind of the end. The exercise, I'll kick up the standard exercise sheet. Which is okay. Okay, fine. Sorry. There we go. So the so I've given you a version of the traffic model, traffic armor that uses MPI put for all point-to-point communications. You may find useful. I would suggest this. However, I think if I remember rightly, I think I give a solution. Just check what we do. I think you should have a copy link there. I said I was a subtlety for Fortran programmers. So this is what you have to do if you're a Fortran programmer. The subtlety is, there's a slight subtlety for Fortran programs. If the memory allocation routines return a C pointer, and you need to convince the compiler it really is a proper Fortran array. So the way you do this is you use one of these ISO-C binding things. You declare a pointer, which is the shared array, and you have a base pointer, which is the C array. So what you do is you call the MPI win allocate shared, and it gives you back this base pointer, which is a C pointer. So that's just your raw address. But then you have to convert this into an array and use this ISO binding routine CF pointer, which says convert this base pointer into a proper shared array of size n. Okay. And then that then gives you a proper Fortran array. Unfortunately, my program relies on the array indexing going from 0 to n+1, not 1 to n+2. And this CF pointer routine is daft. It doesn't allow you to specify the starting. If you create an array with CF pointer, it has to start at 1. So to get an index, you have to then play around with pointers to get an array. It's a bit of a hole in the Fortran standard. Anyway, this is what you do it. MPI Win Allocate Shared, even in Fortran, just gives you back a raw memory address. It's up to you to coerce that into a proper Fortran array. So that's in there. I will just check. So if I will share the correct window. So if I wget that, the traffic RMA, okay, so there's lots of stuff there. So what have I got? I've given you a C and a Fortran one. Let's go into the C one. And I think there is a solution here. Yeah, there's a traffic RMA.c which does, sorry, traffic RMA.c which does the traffic model using puts and gets, but there is a traffic SM.c. I've given you a solution here, which you can maybe look at if you want to, which actually does the shared memory stuff. So it does all this node com stuff. It does MPI Win Allocate Shared, and then for the halo swapping, it does, yeah, MPI Win Fed. And so I mentioned this. We have to check we don't over we don't over index on the wrong array. So I only I do the, so you have to be careful that I only do the direct copy on. I don't do the direct copy on the ranks which are at the extreme ends of the node, because they can't over index them. So basically, and then I do a fence here. So this is the stuff which is do the direct read and write on a node, and then I have to basically do, yeah, if I am on the very left or the very right of the node, I have to do send and receive. So it's again. So I have given you a solution there. So yeah, that's so. Just so that's all in that traffic RMA. There are shared memory solutions there which do work. So there is a working example there, but the exercise still stands. So so I'm around for that. That's the end of the lectures. I'm around until 4 p.m. So I'm happy to, I'll be online. I'm happy to, if you have any other questions, or if you want specific, if you have specific questions, the best thing to do is to do a one-to-one chat. So if you want to discuss code, your own code, or some other code, or some other related problem, or something that's cropped up, just pop something in the chat, and I can do a breakout room, so we can just chat and screen share privately. So that's if I'm around here for another 3/4 of an hour. If you had any questions you wanted to ask, either related to the course or more general, I'm happy to chat to you in the next 3/4 of an hour.